Hello and welcome to another ADLC digital lesson. Today we investigate changing concentration on the decomposition of hydrogen peroxide. Hydrogen peroxide, chemical formula H2O2, decomposes into water and oxygen, but the rate at which it decomposes is partly dependent on its concentration. Hydrogen peroxide is rarely used undiluted. In its pure form, it's powerful enough to be used as an oxidizer for rocket fuel. Usually, it is found diluted in water. For example, you can purchase hydrogen peroxide in 3%, 9%, or even 35% solutions. The higher the percentage, the higher the concentration. A higher concentration solution has the potential for a faster decomposition reaction. One way to think about this is if someone asked you to fill a duffel bag with $100 bills from the floor using only your hands. If there were only a few bills on the floor, that is, a low concentration, the speed you can fill the duffel bag will be limited. However, if there is a large pile of bills, that is, a high concentration, you will be able to grab handfuls and fill the duffel bag much faster. So now we will return to real chemicals, and we'll test if hydrogen peroxide decomposition is indeed dependent on concentration. In this experiment, we're going to investigate the effect of concentration on a decomposition reaction. Specifically, we have two different concentrations of hydrogen peroxide. In one container, I have 0.3% hydrogen peroxide. In the second container, I have 3% hydrogen peroxide. So this second container has 10 times the concentration of the first container. Now, hydrogen peroxide decomposes into water and oxygen, and it does so slowly, but we can speed that up with a catalyst. And a really good catalyst for this reaction is yeast. So what we're going to do is put exactly 2.5 milliliters in each one of these containers, and we're going to then time the reaction for 1 minute and see how much the temperature changes. And we'll also observe to see how much bubbling takes place, because again, remember, this reaction, this decomposition reaction, produces oxygen. So let's get started by measuring the starting temperature of the first container. And let's get this started. And we see that the temperature is 19.5 degrees. So we'll add our 2.5 milliliters of yeast, hit the timer, and then we will stir gently and see what happens. Well, if we look at our container closely, we'll see that there are some small bubbles forming inside. And after about 20 seconds, it looks like we have about a centimeter of bubbles in there. We also have an increasing temperature. The temperature is now up to, looks like 20.5 degrees. Okay, we have 20 seconds left, and the temperature continues to rise, and we have probably about 2 centimeters of bubbling in the container. Okay, 10 seconds left, and we're almost done. And it looks like we're done. And we have reached a temperature of 21.1 degrees. Now we'll just repeat that. We'll rinse our probe, place it into the second container. And again, we've got a starting temperature of about 19.5 degrees. And we'll add our 2.5 milliliters of yeast. And we'll start our timer. Now we can see right off the bat that even after 5 seconds we've already got a centimeter of bubbling. And the bubbling is a lot more violent. Just going to continue to gently stir like we did before. If we look at our temperature gauge, we can see that the temperature is rising very rapidly. And we've probably got about 4 centimeters of bubbling in our container. Okay, with 10 seconds left, we see that temperature still rising considerably. And timer's almost done. And after 1 minute, it looks like the temperature has gone up about 14 or 15 degrees, much more than the 0.3% solution of hydrogen peroxide. So in conclusion, it seems that a higher concentration of solution will result in a much more vigorous decomposition reaction when a catalyst is added.